I'd like to introduce our first invited scientist tutorial. This is Dr. J. Michael Ruohoniemi, or Mike. Mike was actually my PhD advisor at Virginia Tech. I had PhD co-advisors, Dr. Joseph Baker and Dr. Mike Ruohoniemi, and they worked together to run the Virginia Tech Superdarn Lab. And so Mike, Dr. J. Michael Ruohoniemi, he is a professor of electrical engineering at Virginia Tech and the principal investigator of the Virginia Tech Super Dual Auroral Radar Network, or Superdarn Laboratory. Dr. Ruohoniemi earned his Bachelor of Science from the University of King's College and Dalhousie University in Nova Scotia in 1981, and his PhD from the University of Western Ontario in 1986. After graduation, he joined the team at Johns Hopkins University Applied Physics Laboratory that developed HF radar into the Superdarn concept to study the auroral high-latitude ionosphere. As a faculty member at Virginia Tech, he has led a consortium of universities in building a chain of Superdarn radars at mid-latitudes across the United States. His scientific publications now have over 9,700 citations. Today, 12 of the more than 30 radars in the Superdarn network make continuous observations of mid-latitude ionosphere in both hemispheres, and these observations have been instrumental in advancing mid-latitude ionospheric science in numerous studies. So that I'd like to welcome Mike, Dr. Ruohoniemi, to the HamSci workshop, and we are very excited to hear your presentation on mid-latitude ionospheric physics.
Okay, thank you, Nathaniel. Does this mean I can grab control?
You can take control. You have 45 minutes, including questions.
Give me a 10-minute warning, would you?
We will give you a 10-minute warning.
Thank you for the introduction, Nathaniel, and to the meeting organizers for this invitation. You know, it's a real credit to HamSci. It was a year ago that all this came down on us, the pandemic and the restrictions, and there was real gloom, I remember, this time of year about coming meetings and travel. And the first thing that came along that kind of turned that back was HamSci, this online meeting. And it not only took place and was an inspiration and a model for following meetings, but it demonstrated the advantages of doing this, that it can go out to a much wider audience in different time zones without the travel. And it could even engage people like me who are academics who are tied up in the middle of a teaching semester. And I was really grateful for that. Now the topic here is mid-latitude ionospheric physics, which is huge. And I realized as I started putting this together that I can't possibly cover this topic in 40 to 45 minutes. So I'm going to sort of cherry pick some topics that are familiar to me and I think of interest to HamSci. Whoops, I am not getting, there we are. So I have to say something about Nathaniel. Yes, as Nathaniel said, I'm here at Virginia Tech. The research group arrived here about 12 years ago, and Nathaniel was one of our first graduate students. I remember this. Joe and I were sitting in a side office preparing to interview students who might have an interest in working with our group. And Nathaniel came to us as a ham, working with HF radio, very familiar with the principles of HF propagation. That was extremely interesting to us. The talk went very well. Nathaniel was already conversant on many of the themes of HF radio and related science, and things really took off from there. He joined us at a very interesting time too, because we were just going into radar building mode. Nathaniel was easily the best traveled of our graduate students. We really did see him go off to all the corners of the world, like you can see from this slide. Blacksburg, by the way, is located in this southwest corner of the state of Virginia, about a 4-hour drive to Washington. What you see here is Nathaniel on the upper right-hand side. He wintered over in Svalbard, about 80 degrees north geographic latitude. He traveled to Antarctica to participate in the repair of a radar at McMurdo Station. He also made it to Adak, out on the tip of the chain of the Aleutian Islands, practically off the map as depicted here. He has a restless spirit, and that was great. He had some interesting ideas, and one of them led to HamSci. This was the first paper. He put it together pretty much on his own, showing the impact of a solar flare on shortwave propagation paths as observed in the reverse beacon network. And that was the genesis of HamSci and this collaboration between, like say, radio amateurs and scientists, which you see has really taken off. Okay, so 4 basic categories to this, and as I said, I'm going to have to cherry pick the specific topics that I cover. First of all, start from the beginning. The Earth has an atmosphere. That's what gets us started. Oh, and by the way, it's a vernal equinox today, everybody. So get out and enjoy the spring weather. The Earth hangs in space as this beautiful blue-green ball with white swirly clouds over it. The atmosphere is the seat of weather type activity that's very familiar to us as we live on the surface of the Earth. And then beyond that, there's an electrical environment, which is the neighborhood, the geospace neighborhood of the Earth, which also has its weather and variability. Not evident here, but measurable with various techniques. Now, the atmosphere is a mix of gases. If you look at this chart, look over to the right-hand side, that would appear to be everything that's really significant in the atmosphere. Molecular nitrogen, molecular oxygen, atomic oxygen. Really, the atmosphere, if it were all summed up, consists mostly of nitrogen and oxygen. And it really is only of any significant density in terms of supporting life right at the surface of the Earth. Even by 20,000 feet, you're starting to run out of breathable atmosphere. And if you compare that to the dimensions of the Earth, 63, 70 kilometers in radius, the atmosphere is very thin. It really is just an envelope that wraps around the Earth. And a somewhat surprising fact that I quote to my classes is just to give us a bit of perspective. If all that atmosphere were compressed to the temperature and pressure at sea level, it would only be 8.5 kilometers thick, or about 5 miles thick. It gives you a perspective on this, that how very thin it is, and perhaps vulnerable. You know, if one were to drive through it at normal highway speeds, you would pass through the entire depth of atmosphere in 5 minutes. Kind of a sobering thought. And there's a lovely shot there from the ISS with a spectral type crescent moon in the background, and you can see the transition from the top of the clouds through the blue of the sky into the black of deep space. Now, as it was mentioned yesterday, the atmosphere, of course, has layers. We're very familiar with the troposphere. The one point I want to make about this is the classification of the atmospheric layers. It's done according to the variation of temperature with height. So in the troposphere, as we're all familiar, the temperature goes down as you go up in altitude. When we climb the mountains around Blacksburg here, we're very aware of the cooling effect of going to higher altitude. That reverses at the tropopause, and then the temperature actually rises, and there are subsequent falls and rises. Each of those expressing some interesting physics going on in the atmosphere, either a heating source or a loss, energy or a heat loss mechanism. And the particular mechanism in the stratosphere is the absorption of UV by ozone. And I also think of that 3.6 degree Fahrenheit per 1,000 feet of latitude as kind of another sobering factor. It's again an expression that the atmosphere is thin, and that as we go up in altitude, we rapidly run out of it. We run out of breathable atmosphere. We even run out of sufficient warmth in the atmosphere to sustain us. Okay, so what's going on here? If we look at the left-hand side, which seem numerically insignificant at first glance, I mean, this is an exponential scale along the x-axis, and over here on the far left, we're many orders of magnitude down from the sorts of densities that are associated with molecular nitrogen and oxygen. These are ions and electrons. A number of varieties of ions in play here. Of course, an electron, a bare electron, is the source of negative charge and it exists by itself. Well, there are some negatively charged molecular ions, but they're not significant for these purposes. And you know, the densities here are very low. Even as you get up to the altitudes where we talk about the ionosphere and HF radio propagation, we tend to think of it as a, you know, ionized plasma supporting HF propagation. Still, the neutral atmosphere is dominant. And as we've heard in this meeting, that there are important drivers for physics in the ionosphere in the neutral atmosphere, which have really only become highly appreciated in the last couple of decades. Phil was talking yesterday about the importance of waves and things propagating upward into the ionosphere, causing disturbances. And this is an active research area. The actual coupling, or the way that the atmosphere, neutral atmosphere, and ionized species interact is turning out to be a very productive line of research. Well, despite the fact that the densities are so low, it's sufficient to give the atmosphere electrical properties and make it very interesting for us. And so the ionosphere, and I think this audience probably knows this, the ionosphere is this layer that contains a relatively high concentration of ions and free electrons. And on a day-by-day basis, the dominant source of ionization, charged particles, is the sun. And what's really significant, and the way the ionosphere was discovered and initially researched and continues to be researched, is by its impact on radio waves. It must have been a surprise for the earliest researchers to go out in the field, direct a pulse vertically, and then have an echo come back. There's nothing visibly up there to generate that reflection. And this gives you, this figure gives you actually a view of the ionosphere in terms of the air-glow layer. So there are reactions that lead to glowing particles in the ionosphere. It gives you the sense of a kind of a, well, not a shield exactly, but a wrapping around the Earth, and one can visualize bouncing radio waves off that layer and generating multiple hops that would traverse around the limb of the Earth. One way of exploiting the effect of the ionosphere on radio waves is to do a sounding experiments. And this goes back to the earliest days where you transmit pulses vertically and vary the frequency of the pulses and record their time of return. And that time of return generally increases with the frequency. And by analysis of that, you can get out a profile of the electron density with altitude. This is a very fundamental way of determining a basic parameter of the ionosphere, namely the density variation with altitude. It's been in place since the earliest days, and it remains very, very useful. And the discussion that we've had at this meeting about the Personal Space Weather Station having this capability, and these sounders or ionosondes being able to be moved around, put under other types of instruments to do diagnostics, is very exciting, especially to people like me who are forever trying to get at this information, trying to understand what the density profile is in the ionosphere. Now it's divided into three layers, the D region, and the controlling factor here, it gets a little tricky here, but the controlling factor here we sometimes think of as the shape of the profile, the electron density profile with altitude, with perhaps a well-defined peak at the F layer, maybe a ledge for the F1 region, another peak or maybe ledge for the E region, and below that the D region, with significant densities being encountered perhaps by 50 kilometers or so. It somewhat varies. Actually, the more controlling thing here is the nature of the charged particle motions with altitude. And we have to remember that charged particles, they have this property that they feel the magnetic field, they feel the electric field. The neutral particles do not. They move along and they feel winds and pressure gradients and other things going on, but they don't directly feel electric fields and geomagnetic field. A lot of interesting physics happens in the ionosphere because the electric fields are generated by various processes, they act on this weakly ionized plasma. They cause the charged particles to move, and there's many things that happen as a consequence of that motion. Now it gets a little, you can follow me on this. The sketch on the lower right-hand side here is demonstrating how the motion of the ions and electrons varies with altitude. So we're assuming the existence of an electric field shown by E. There is a background magnetic field. If we go down to the lowest altitude shown here, well, below 75 kilometers, we have a situation where the density of the atmosphere is so high that basically electrons and ions do not have any sustained motion. If they do get going, feeling the electric field, they immediately collide with a neutral and they lose their energy to the neutrals and they have no sustained motion. As we go higher and higher, the density of the atmosphere drops. The rate at which these collisions happen, it also decreases. Now the electrons and the ions, well, starting first with the electrons, they start to have some significant motion, initially in the direction of the electric field. But as we go up to even 80 kilometers, you can see that that direction is shifting around. It's no longer parallel to the electric field. It's shifting to orthogonal to the electric field. By the time we reach 100 kilometers, it is exactly orthogonal to the electric field. So you've had this swing of the electron velocity vector with altitude that went through 90 degrees from, say, 75 kilometers or somewhat below it to 100 kilometers. Big swing in the electron velocity and a big increase in the electron velocity as well, because you're getting out of this collisional regime that is a result of the neutral atmosphere. Now the ions do something similar. That's on the upper side of this plot. If you go down low enough, they're having even more of an issue of collisions with neutrals. You know, the ions are physically larger and they have larger cross sections for these collisions. A similar thing is happening with the ions, but it happens at higher altitudes and more slowly. So you don't get the balance between processes until 140 kilometers with the ions, and they don't get to going orthogonal to the electric field until you reach an altitude of 180 kilometers. And so in these transitions in the ways that the electrons and ions move, we have the essential physics or dynamics of the D region, the E region, and the F region. One significant consequence of this is that when we get differences in velocities between the ions and electrons, then we have electric currents. If you combine that with significant density, then we get electric currents. And that leads to measurements that magnetometers can make, and things like induced electric currents in the surface of the Earth and in power lines and pipelines and things, leading to very significant space weather effects. Okay, so returning to looking up at pictures of things, another source of ionization, of course, is the Aurora impact ionization. Energetic particles are spiraling down magnetic field lines. They collide with particles in the Earth's atmosphere. They knock electrons free. There's recombination, and we get these lovely flowing colors, which is indicating a level of activity that couples to processes in the Earth's space environment that I'll talk more about in a moment. Now I want to get on to talking about the regions of the ionosphere. It's not all the same from the pole to the equator, and it's not all the same because of all this electrical activity or the electrical properties of the ionosphere coupling to the Earth's space environment. This is an image taken from a satellite some decades ago that gives you a comprehensive view of what we call the auroral oval. So this is where particles have access to the Earth's upper atmosphere. You see it glowing here. They can produce aurora. These isolated arcs and bands that you see as aurora, they actually coalesce into this coherent feature that goes at around to all local times and has some variation in size with longitude. And this is where we have direct access, as I was saying, of energetic particles to the Earth's atmosphere. And you see that there's boundaries to this, and there's distinct regions that are defined by it. We call the glowing band region the auroral zone with the auroral oval. Inside that, we have the polar cap. It's like the hole of the donut. Equator to that, what's variously called the subaraural ionosphere, getting below that edge of the auroral oval, or the mid-latitude ionosphere. And then below that even, we have the equatorial zone. And this map doesn't extend to that. There's interesting physics there that I'll just have to wave at in the interest of time. So here we're talking about the mid-latitude region. And at a glance, you look at it and you say, well, looks rather dull, black and unlively. Wouldn't you rather go to the auroral zone where there's going to be activity all the time and quite variable and spectacular activity at that? We'll get back to address that point. Now I want to talk about our technique of Stormdarn for sampling the ionosphere, making measurements and doing research. We are basically a ham radio system on steroids. You know, we operate on the same principles, and we're exploiting HF propagation for the same reason, to reach to very far ranges. Refraction in the ionosphere at HF frequencies bends our rays to the horizontal. They can propagate by that mode to great distances, or they can do multi-hops. They can refract to the ground and then be forward scattered and perform another hop. And on one of these hops, they may encounter irregularities in the plasma of the ionosphere. Irregularities can be thought of as waves in the density. And if there's a right match between our radio frequency and the wavelength of these waves and the density, then we get constructive interference. We get a strong signal coming back. It's like pushing waves in a bathtub in the old days. There are ways to combine our frequency and the wavelengths of the irregularities to get a strong signal. And we can do this because the irregularities have such large cross sections that with our low power system, we actually get significant signal back. So maybe operationally, the main difference between this and a ham system is that we're not communicating with somebody on the other side of the world. You know, that would require a hop coming down to the ground. We're communicating with the ionosphere. We're getting, our baseband is whatever modulation the ionosphere puts on our signal. So the modulation would be on amplitude or on frequency. So we're getting Doppler shift and we're getting signal to noise ratio, and we're making something out of that. We're doing studies with it that express things that are going on in the ionospheric plasma. Now this is an image of data from the radar in Northern Ontario in Kappa's casing. Oh, hi Gregory, I saw you buzzed in from London. That's my alma mater, is University of Western Ontario. I am originally Canadian. This is showing a single 2-minute scan of data collected with that radar. It's performing an azimuth scan across this sector, and it's at high latitudes. And it was located there to look across the auroral oval because, as I said, it's obvious that that's always active and generating lots of, potentially generating lots of signal for our system. And certainly it was doing that here. The gray band is ground scatter. So here we come down to the ground. If somebody were down there with a receiver, they could hear our waveform coming through. And we have actually done that. But our prime interest here is what you see in the velocity data. It's color scaled for velocity. This is from the Doppler shift of the signal as it's returned to us, and it's a simple Doppler shift. So if it's blue shifted, it's motion towards us. If it's red or yellow or green, it's motion away from us. And what you notice about this is that there is a regular pattern in the velocity shifting from away on the left to towards in the more easterly. You can kind of figure out what the overall velocity vector is from that variation, or you can combine it with measurements from another radar and figure out what the two-dimensional velocity is. You also should take note of the magnitude of the velocity. This is not like winds in the neutral atmosphere that might be 20 or 30 miles per hour. This is 1,000 meters per second. 100 meters per second is a smallish velocity. 1,000 meters per second is common. 2 and 3 kilometers a second are even encountered. So these are spectacularly high velocities in this ionized plasma, and that can only be driven by electrical processes. So combining measurements from a number of radars, making velocity observations like this, we can put together what amount to weather maps. These are showing, if you like, the winds in the plasma, only these winds are moving at kilometers per second sorts of speeds. We don't have coverage everywhere. As you look at this, you see that there are gaps. So as has been discussed in this meeting, we do some things where we combine our observations with a background model and synthesize a overall map of what the plasma winds are doing, what the plasma motion is. We have radars in both hemispheres, so you're seeing a view of the pattern in the northern hemisphere on the left, the southern hemisphere on the right. And you see that it's primarily a two-cell pattern with the sun up to the top of this slide. The motion across the center of it, across the polar cap, is anti-sunward in both cases. And then it closes around the flanks and that cycles around again. Now, these are, as I said, electrically driven processes. So we're not looking at barometric pressure to describe this. It looks like pressure cells, right? Positive and negative sort of pressure cells. These are pressure cells, but the pressure here is voltage. It's electrical voltage driving this system. And we can characterize these patterns in terms of the total potential drop across them, which in this case is indicated for the northern hemisphere as 109 kilovolts. Now, the value of these is that these maps is that it's showing something very important about the coupling of the solar wind into Earth's space environment, beginning with the magnetosphere, which is that volume of space that's carved out by Earth's magnetic field, where things are dominated by Earth's magnetic field. It begins with the sun throwing off its own plasma, magnetized plasma that collides with the Earth, shown on the right-hand side. All sorts of interesting coupling processes occur across the boundary that separates Earth's magnetosphere from interplanetary space. One of those things is to set up the motion of plasma in this large volume, which mirrors effectively in the ionosphere. So one of the reasons for this research interest is not just ionospheric physics, not just to see what's going on in this few hundred kilometers of the Earth's lower atmosphere, but we actually have a screen here for seeing what the motion is of plasma through this enormous volume of space that's carved out by Earth's magnetic field. And to get a sense of the scale of that, on the lower right-hand side, I've drawn in a small red circle around the Earth, which represents the ionosphere, the lower part of the ionosphere. And you can see that having instruments on the surface of the Earth, that's very accessible to us, and we can make observations across that that can then be projected through this whole volume and help us address problems in understanding space weather and the overall process of how energy and momentum couple from the solar wind into the Earth's upper atmosphere. So a few text slides here. What I'll highlight is that the mid-latitude ionosphere is generally thought of as a buffer zone. Below 60 degrees and above 20 degrees in both hemispheres. Nothing too much is supposed to be happening here because probably there's no obvious reason to expect a driver for activity. High latitudes are very active. There's an equatorial band that's also very active that has its own interesting physics. So that leaves the mid-latitude ionosphere to be neglected. And I think for a number of decades, perhaps it was. But this view has changed dramatically in the last 20 to 30 years, in large part because of space weather and also because instruments have been deployed that have made surprising observations, including our radars. As you know, most of the world lives at mid-latitudes. We all do here in the mainland of the US. And harmful impacts of space weather, although they may be more infrequent here, are potentially more costly because of the concentration of people and assets at these latitudes. And then it turns out that the mid-latitude ionosphere is not so quiescent, not so passive and just sitting there. Turns out it has lots of interesting physics, which was known to people who were doing experiments with these awesome incoherent scatter radars. Going back to the salad days for Arecibo here, these are magnificent instruments that are sited at mid-latitude locations that do comprehensive diagnostics of the ionosphere. They measure, in addition to velocity, density, and temperature, and they can be related to composition and winds and all sorts of amazing things. These are very powerful and expensive instruments, and they make the sorts of complementary measurements that we need to interpret our observations. So looking at mid-latitudes, what's interesting about them? Well, sometimes you simply have auroral processes extend to these latitudes because you get a big disturbance. This is a map showing the prediction of the expansion of the auroral oval over into the northern US states. This is from a storm that happened in the last solar cycle that was observed from here. A photograph was taken from a nearby mountain looking off to the north. You see the low glow of yellowish green auroral lights. This is when you hear about Aurora occurring in Texas. It makes the evening news that there's been a solar disturbance and people have a reasonable expectation of going outside and seeing Aurora, and there may be some consideration given to possible space weather upsets in technological systems. Well, we had some issue in the early days of Superdarn, all being located at auroral latitudes. An initial Superdarn here, or Superdarn Classic, if you like, shown in the blue radar outlines. This is meant to follow the auroral oval. We were in fine shape for quiet conditions and moderately disturbed conditions, but when we had a major storm going on and that oval expanded, as people who live farther north will realize, the aurora rises in the sky, it's overhead, and then you actually turn around and look to the south to see the aurora. And our radars could not follow that. So our solution for it was, right, let's locate radars in another tier, south of the auroral tier of radars, in order to catch that expansion of the oval, in order to follow all the exciting things that are going on when you have a geomagnetic storm. And so we proposed to build one or two radars on this basis, and we actually called it Stormdarn, with the idea of, you know, we'd only really see something when there was a major storm going on. So the first three radars built at these latitudes are shown here in orange. The very first one was at Wallops Space Flight Facility. Another one is in Blackstone, which is not too far from here. Another one by partners in Japan on the island of Hokkaido. Now, it worked as advertised. When we have big storms, and this is a movie showing velocities inferred from our analysis, and I'll skip the details of it, but this is a storm period that's showing the expansion of the flows to low latitudes, to about the 49th parallel or so. And this is these are images that are being taken at a 10-minute step. We actually have data at higher resolution than that, but just to cover it. And you can see how very expanded things are and the variability that's going on, the velocities. So Stormdarn works. We can collect the data, we can observe the expansion, we can see all the stuff that we couldn't see before. And as I said, there wasn't really an expectation that we would see anything during non-storm periods. We set up that first radar, started making observations, and we're immediately surprised to see categories of scatter that we hadn't anticipated. And one of these was something called Say's subaraural ionospheric scatter. And this is an image of the velocity pattern associated with one observation of this type of scatter. This is the radar in Blackstone. The scatter region is over the Great Lakes. You see from the color coding that there's some velocity associated with this. Now looking at the scale on the right-hand side, you see how small the velocities are compared to the auroral flows that we're looking at before, which were like a kilometer a second. These are tens of meters per second. They're much lower velocities. We're out of the auroral zone. We're away from the powerful drivers for plasma convection that exist at higher latitudes. But there's something going on here. And it took us months to wrestle this down because our prior way of analyzing the data would have ascribed this all to ground scatter, that this was from a hop because the velocity was so low it couldn't possibly be ionospheric flow. We hadn't made the adjustment to the different physics of the mid-latitude ionosphere. This is definitely plasma in motion in the mid-latitude ionosphere, and it has its own drivers and it has its own physics. And frankly, nobody quite knows what's going on, what's driving it, what's even generating the irregularities. So one of the things we can do is combine our velocity measurements from adjacent radars, and here we have line of sight velocity measurements from 4 radars, and I'm just showing them here where there's significant overlap between the vectors so that we can combine them into this map of the two-dimensional velocity. This is not quite a conventional arrow. The circle is the base of the vector, and what you're seeing here is an eastward flow. And there's some velocity variation across this. We can run this at 1 or 2 minute steps. I guess these are 2-minute scans. And that initial eastward velocity, as you can see over this period of 20 minutes, does a dramatic flip to westward. These flows are not terribly high compared to auroral latitudes, but you know, they are still pretty good, 100 meters per second or so at their peak. And you can actually see how this transition occurs. It seems to be coming up from the equatorward edge and moving through it. And frankly, there's no explanation for this. Well, we have thoughts and speculations about what's driving the flow, what causes it to flip like this, but it's very much an active research area. So Subaru expanded to mid-latitudes. Nathaniel was a part of this, where we built out the chain starting from Virginia, the two initial radars. We built it out going to the west to Kansas, to Oregon, pairs of radars in those sites, and then an ADAC on the Aleutian chain. And there were other activities going on at higher latitudes. And since 2013, this has been built out even further into the Asian sector. I can't let this pass without showing a picture of one of our radar sites. This is Hayes in western Kansas. Very large antenna arrays. These are, of course, wire antennas. And there's 2 antenna systems deployed here. You can see that from the way they join up. There's an antenna system looking to the northeast and another one looking to the northwest. So these are looking off into volumes of space where they overlap with fields of view from adjacent radars. And that's where we build the chain up. That's where the dual Aurora radar network part comes from. The dual from the fact that we can combine measurements from adjacent radar systems.
10 minutes, Mike.
Okay, thank you, Nathaniel. Okay, so this led to new views. And I want to make the point here that the value of what we see here is really very much enhanced by combining the observations with those from other systems. We realized quite a bit of benefit from working with the Haystack Observatory group headed by Phil, and also from working with records of total electron content that are derived from the GPS system. And I'll give you an example of that here. This is an observation of what we call SAP, subarrow polarization stream. This is a feature of the ionosphere that exists at that boundary between the auroral zone and the subarrow or mid-latitude zone. And this image gives a nice overall view of the several things happening. The SAPS is this high velocity channel with the saturated red and saturated blue. Very narrow, it's like an arc. It sits there over just a degree or two of latitude, very strong flows from mid-latitude location. And polar to that, you can see more moderate flows in the oval, and equator to that, lower flows still happening in the southern auroral ionosphere. Combine the measurements from all the radars in our mid-latitude chain across the US, and you get this very big dramatic picture with alternating bands of red and blue at the equatorward edge, which is consistent with the radars looking to the west and to the east, observing a westward flow, so that flow reverses from being towards the radar to being away from the radars as you alternate the orientations of the radars. And this is the first time that we were able to manage such dramatic views of this phenomenon and put it into context. In this case, looking at what we have available to us from GPS measurements for measuring essentially the thickness of the ionosphere. How much plasma do we have within particular volumes of the ionosphere? And looking at this, you can see a bluish region, a zone where density is depressed, called the mid-latitude trough. And if we overlay things here, it's identified with these arrows, it turns out that our SAPS feature lies within that trough, and it clearly is controlled, or it's part of the system of densities and currents and electric fields that are all kind of ordered by the geometry of the trough and the Earth's magnetic field. Now, some work that we did with Millstone Hill, there's this question out there, you know, how do we understand the SAPS? We can measure the velocities. Why is it there? You know, why does it exist? And then what's responsible for the irregularities that we see? Why are we seeing backscatter from this thing? And understand that, you have to go into the plasma physics. You have to know something about the plasma parameters, and that's where the incoherent scatter radar comes in because of the comprehensive suite of measurements that it provides. This is a map of electron density created with Millstone Hill across a trough type feature. I won't show the radar data because it just sort of sits and complicates things. But there is a trough in here. We did see SAPS type flows within that region. We can extract the profile of electron density across it. And now we can address this issue, what causes the irregularities in the backscatter. Go to our inventory of plasma instabilities, mechanisms that cause these plasma waves to emerge, and try to apply these ideas to the observations. We made an initial cut for this set, for this particular experiment. We had a proposition for what could drive the formation of irregularities, but in the end, it just didn't work. And this question is very much open and out there and being worked on. Okay, so the last theme, and I'll just go through it here in a couple of slides. Very recently, we started doing biostatic observations with Stormdarn radars, using the radars in Oregon and in Kansas, where the Kansas radar transmits, the Oregon radar receives. This is simulating really a ham radio type of link, but we're interested not only in the direct mode of observation, but also in forward scattering off irregularities or off the Earth's surface. The upper figure is showing geometries for particular propagation modes that will make the connection between the two sites. And in fact, we have assembled observations now that demonstrate the viability of all these modes. One example is shown in the lower right-hand plot. 4 radars are in play here. 3 of them are running in the standard by themselves mode, monostatic. They just send and receive their own signal. And you can see gray bands corresponding to ground scatter. And then superimposed on that are those yellow outlined areas. And that's where bistatic observations are being made. Namely, the one radar is transmitting, the other is receiving. We have something happening in the side lobes between the radars. That's like a direct connection. We're also getting something at this time in terms of the ground scatter mode. So signal going to the ground, reflecting off the ground, and reaching the other radar. And this is very useful and an interesting test of our operations. And it gives us insight into what the structure of the ionosphere is. So this has primarily been led by Simon Shepard out of Dartmouth College. He's put together this lovely looking figure with the ray tracing through sample cuts of the ionosphere provided by IRI. And by iterating on this, we can satisfy ourselves that there are these propagation modes available at this time of day to support the bistatic observations. Okay, so I'll conclude here. I don't have that many answers to give. I ask a number of questions, and this is common to us all, I think. Some of these are more on the science side, some more on the operations side, but there's definitely overlap. A couple of these that I want to highlight. I've wondered this since early on. We get these structures that clearly are capable of scattering HF signal. Is this in play for hams? Do you guys see this? Do you sometimes get better observations between 2 sites that are to the east and west of one another by turning your antennas to the north? Because there's something up there that will reflect the signal between your 2 sites. I don't know the answer to that. And then the second to last bullet here, we've been talking here about how do you combine data collected at a few sites and get something out of it. You can approach that another way. The data may be very sparse, and the inversion of that into a large-scale map may be kind of difficult and unsatisfying. But if you start with a model of how things are working, those data, although they may be isolated, could be very relevant to the testing and development of the model. We're doing that with the solar flare observations that Shivaji was talking about yesterday. And it's giving us some way of making decisions about how to drive the models in order to more realistically generate results, simulated results that reproduce what we see in our observations. And so the ham observations can also be applied to that. they are expressing the physical reality of what's happening in propagation, and any model that wants to perform that task needs to be reconciled against those observations. Okay, so with that, I'll stop.
Thank you so much, Mike. That was a wonderful review of mid-latitude and high-latitude ionospheric physics. And I really appreciate you giving us those questions at the end, because that's one of the things we're really trying to think about here in the HamSci community is, you know, we have lots of observations. The amateur radio community has lots of engineering experience. But guess how do we connect our observations to the real science questions? And what are the science questions that need to be answered? So I think this is great. Let's see a few comments here. It's an excellent tutorial, Dr. Ruohoniemi, and very informative. And we have a couple of moderators. I think at least one of them you know quite well, Dr. Phil Erickson. He's
Right.
going to, and we also have Diego Sanchez, my student. They will pull out some questions from the chat to ask you.
Yes, Mike, I owe you some things for the very kind measurements, mentions of A stack. Let's see. There is a question, an interesting question from, I'm going to kind of pick out randomly here, from Bill Ongelke, which basically said, you know, making a contact between a station to the east and the west, to the station to the west by turning antennas north is known to happen at VHF frequencies, but you're talking about HF, I assume.
Yes. Is it observed at HF frequencies?
Okay.
VHF off Aurora is, you know, I think the first observations were in the Second World War, around that time that amateurs in Europe realized they could point their antennas to the north and get better reception. And I would propose, or as I've said, I've wondered, when you see these large SAPS features, for example, stretch right across the continent, if you know that's going on, is there some experiment you could run where you point to that, knowing what the angles are, and generate this sort of side scatter link? It's what we're doing using ground scatter, and we'll have used some ionospheric scatter between the two radars in our biostatic observations, because that's essentially operating in that kind of mode. So yes, the question is, does that work for HF at mid-latitudes?
You know, we have some members of the community like Tim Duffy that have these large contest superstations, and he has asked what are some ways that we can help answer questions. That sounds like the sort of thing he might be able to help test.
Right. Diego, if you don't mind, I'm gonna pull one more question out. This is from Ben Vitfleet, who is in Europe, of course. Mike, he says, Mike, at night on 7 megahertz, when the critical frequency has long dropped below 7 megahertz on a short NVIS path, like 200 kilometers between stations, he still sees scattered signals 20 dB above the noise, and he wonders if that might be ionospheric scatter.
I think it's very likely. I do wonder sometimes when sometimes these maps they show you have a link at station here, station there, and a line is drawn between them. Did the signal really go across that line, or did it find some other way to make the connection? But I think that's very possible. Europe is mid-latitude geomagnetically. We don't have the coverage yet at mid-latitudes from Subaru to compare with. But yeah, I think that's definitely a consideration there.
Great. Diego, would you like to pull a question or two?
Yes. So there's a question from Ronald Kamon. I apologize if I mispronounced that, but how do you calibrate the radar systems for the plasma velocities?
Well, we have a coherent radar system. We look at the Doppler. We mix the return signal with our reference signal in our coherent receiver, and we can detect Doppler shift from just the difference in the signals. You know, you can think of a straightforward IQ system. We're not doing that much anymore. We're doing it more digitally, but it's basically the same concept. The calibration that we have trouble with it's kind of odd, is getting the sign right. because there's a number of places in the hardware and the software where the sense of the sign sort of flips. And if you're not careful about that, what you think should be coming towards you is actually receding. And the calibration is often consists of this. Fire it up. Is the scatter going in the right direction or the wrong direction? And then you can deconstruct it to see where you lost track of the sign.
That happens at Millstone too, Mike, so please don't feel bad. It's more common than you might think, right?
Yeah.
Diego, do you have any other questions?
I only see one more question by Jonathan Rizzo. With wavelengths so long and transmitting antennas so inefficient, is a VLF radar practical?
Is a VLF radar practical? Do you mean with this antenna system, or do you mean to go to that as an alternative to this system?
As an alternative, can you design a VLF radar even though the antennas would be very inefficient?
I think that's what he means. Yeah.
You know, using these antennas, I mean, VLF systems are
completely redesign.
Yeah, in other words, he's basically saying, is it possible to even get enough gain to even know where you're looking with a radar at VLF frequencies?
No, actually, I wouldn't think so, no. We're at the limit of what's practical to build for a 10-meter system, you know, or something running on 10-meter signal. This would become like an isotropic antenna for a VLF system.
Right. I'm looking myself. Just a comment from your colleague Bob McGuire, who says he sees skew paths, you know, not direct between stations on lower frequencies, 160 meters, 1.8 megahertz all the time. And especially if you have a directional receive antenna, it's pretty obvious to him. So, you know, at your lower frequencies, you guys don't scan down that low normally, I know, but.
Yeah, well, we lose directionality as you go down in frequency, so that's one concern. And our antennas are not putting much power forward as we go down in frequency below 8 megahertz, so that limits us. But it is clear that more modes open up as we go down in frequency. Things get more complicated and difficult to make out, which is one reason why we prefer to operate in the highest frequency that the ionosphere will sustain.
Right.
Make one more comment about some of these things and comparisons between high latitudes and mid latitudes that we've become aware of, moving between one regime and another, is that things are simpler at mid latitudes in terms of what's going on in the ionosphere. You can hope to make out some of what's going on in the day-to-day ionosphere that's reasonably approximated by the Aurora in terms of propagation and background conditions. When we try to do this at high latitudes under auroral conditions, there's so much variability, so much electric field, so many currents, so much happening that is always very difficult to get at the basic physics. Even with, say, incoherent scatter radar measurements available to us. Mid-latitudes have a big advantage. You can make out things in a more straightforward fashion and get to answering directly some of the physics problems that have been very hard to tackle at higher latitudes. So in some ways, the fact that we aren't as stirred up and colossal in the scope of things at mid-latitudes is actually an advantage, because we can isolate particular features in the ionosphere and examine them and test them against, test our understanding against these types of observations.
Okay, that's a good place to, that's a good lead in to stop. I think we should all thank Professor Ruohoniemi for an extremely excellent tutorial. So Nathaniel, I'll turn it back to you.